So the last day we were looking at sequences and series, and we had just introduced the idea of patterns. And we were looking at the first type of pattern there where we were given shapes. And we did the questions 1, 2, 3, 4 on page 197 in our books. And we said that a pattern was a set of numbers, objects, diagrams that repeat in a particular manner. And each distinct object or number in the pattern is known as a term. So in other words, the fifth term is the position that that object or shape or number holds in the particular pattern. So we saw here that we had a pattern of a triangle, circle, square, and that pattern then began to repeat itself again. So triangle, circle, square. In the second part, then we were establishing whether the third term would always be a square and why. And we were able to see if subbing in for n is an element of the natural numbers, that we were always looking at multiples of 3, and therefore the third term will always be the square. In question 2, we had a different type of pattern, and we also had colours involved this time. So we had triangle, hexagon, triangle, hexagon, and then the pattern begins to repeat itself again because we have a lilac, a violet, a green, and a yellow in terms of colours, and therefore it's a repeating pattern of 4 terms, not 2. In question 3, then we had to just predict what the next term was going to be. And again, that's quite a popular question, so making sure you're able to see what is the next pattern and how is it growing. And as we get into more complex questions later on in the chapter, we'll then set up a formula to represent the pattern that we're actually seeing. So in the second type of patterns that we're going to look at today is where we're going to draw a graph and see what shape that graph is. Now we'll revisit these graphs as we're going through the different types of sequences. So today we're looking at a very basic example. So for example, we have Annie has a money box and she starts with €2 and adds €4 each day. And we have to create a table showing how much money she has over 10 days. So at the start she has €2 in her money box, and therefore we have a total of 2. And then every day she adds €4. So her money box on day 1 is 2, she adds 4, so therefore she has a total of 6 in her money box. She has 6 in her money box, she adds 4, so she ends up with 10. And if we continue doing this, then by the time she gets to day 10, she'll have saved up to €42. So the second part of the question then says, well, using the axis, draw a graph to show how much money she saved over 6 days. So if we plot our points over 6 days, what do you actually notice about this graph? Well, the first thing we should notice is that if I actually was to use a ruler and I draw a line through my points, we can see that the shape of the graph is a straight line. And also, if I do rise over run, or I get the slope of the graph, I can see that the slope is equal to €4. And if I look, the 4 was constant because that's what I was adding every single day. So what I was adding every single day remained constant, and therefore that led to the shape of the graph being a straight line. Now what you should also notice is that it cuts the y-intercept, in other words the y-axis, at €2. And it cuts the y-axis at €2 because that's where we started with. That's what she had in her money box to begin with. So could we extend this graph beyond the 6 days? And if so, what would it look like? And the answer is yes, obviously. We could continue this graph indefinitely because once it's a straight line, that means that it has a constant slope, and we could continue to find out what she has in her money box even on day 100. But what we should notice is that every day we're adding €4. Then if we were to do out a sequence, the pattern representing this graph, and we go back to our numbers there, we can see we started with 2. Then we added 4. Then we added another 4. Then we added another 4. And that continues on. So what you notice is that we always have the 2, and then we're adding on 4 once, then twice, then 3 times. So we're adding on 4 n number of times. However, we didn't start at n equals 1. We started at 0. So therefore, if we're starting at n being 0, and then this next 4, then the next one has 2 4s, then the next one has 3 4s, it's always 1 less than the position that we're holding. In other words, term 1, term 2, term 3, term 4. Term 1 has no 4s, term 2 has 1 4, term 3 has 2 4s, term 4 has 3 4s. So therefore we can actually write this as n minus 1. So in other words, I can find any term in the sequence by saying 2 plus 4 times n minus 1, where we say A is the first term, which in this case was €2, and D was what I was adding on, or what's known as the common difference. And we call that D. So therefore, I can actually say that the nth term can be found by saying A plus n minus 1 times D. And this is for what we call arithmetic sequences, or as you can see from the graph, linear. So this rule will only apply for arithmetic sequences, which is what we're going to focus on today. So we're going to have 3 main types of sequences that we're going to look at in this chapter. The first one being arithmetic. So as we saw in the previous graph there, arithmetic are going to represent these linear equations, these linear sequences, I should say, sorry. The second one will be geometric, and we'll also then have a third one, which is quadratic or non-linear sequences. So when we are looking at arithmetic sequences, what we saw there was that they will always have a constant added to them. So in other words, if I look at any example of an arithmetic sequence, we say that an arithmetic sequence is a set of terms in a definite order where the difference between the first term, or between any term, and the consecutive term is constant. So consecutive meaning one after the other. So the difference between any 2 consecutive terms is constant. So what we say is that T of n represents the nth term. So for example, if I have T5, then that represents the 5th term in my sequence. If I have T1, then we say this is the first term, which we always refer to as the letter A. So we use A to represent the first term. We're going to use D to represent that common difference between any of the 2 consecutive terms in an arithmetic sequence. So that is constant. So we saw if we were to draw a graph, that common difference is the slope. and therefore n is the position held by the term in the sequence. So as we saw there, if n is 5, then that's the 5th term. If n is 6, that's the 6th term. So in general, if we were looking at the first term, we would say it is a. If we were looking at the second term, it would be a plus the common difference. If we were looking at term 3, it would be a plus d. In other words, a plus 2d. If we're looking at the fourth term, it would be a plus d plus d plus d. In other words, 3d. And obviously then, if we go all the way up to the last term in the sequence, it would be a plus, and you can see it is always, the number in front of d is always 1 less than the term position. So therefore it's a plus n minus 1 times d. So we can find this formula in our maths tables, you'll be glad to know, on page 22. But you have to make sure that you're looking at arithmetic sequences, because as I said, we will be looking at geometric as well. And therefore, we don't want to mix our formulas up, which is often what happens. Okay, so the first thing we want to do is prove that a sequence is arithmetic. So we saw in the previous example that obviously a straight line graph would prove that. So in other words, the slope would be equal to the common difference. The second method that we're going to look at now is by using the fact that the difference between two consecutive terms is always the same. In other words, if I subtract T1 and T2, then it should be the same as if I subtract T3 and T2. Or we could say T2 minus T1 would be the same as T20 minus T19. So any two consecutive terms, if I get the difference between them, they should always be the common difference. So for example, if I have 3, 5, 7, 9, and I want to see, is this sequence arithmetic or not? Then what I'll do is I'll write above it T1, T2, T3, and T4. Now it's fairly obvious here. I can see I'm adding 2 to each term, but I'll write down T2 minus T1, and that would be equal to 5 minus 3, which is equal to 2. And then I would say, well, what's T4 minus T3? And T4 minus T3 is 9 minus 7, which is also 2. Or I could even say T3 minus T2. I don't have to do this third set, obviously. And I'd have 7 minus 5, which is also 2. So you can do it for any two consecutive terms, and you should see we always get the same. But of course, you have to make a conclusion here. So we would say, therefore, T2 minus T1 is equal to T3 minus T2, which is equal to 2. Hence, sequence is arithmetic. So let's look at this one here then. We have, again, 1, 2, 4, 8, and 16. So T1, T2, T3, T4, and T5. So if we say, well, what's T2 minus T1? And we say, well, it's 2 minus 1, which is equal to 1. And if I take T3 minus T2, well, that gives me 4 minus 2, which is equal to 2. So this time we can say, well, hang on a second, there isn't a common difference between these terms. We would say, therefore, T2 minus T1 is not equal to T3 minus T2. And therefore, to conclude, we would say, hence, the sequence is not arithmetic. So C then is where we're going to show it's true for all n. And that's where we're given the general term rather than the actual sequence itself. So say, for example, we're asked to prove true for all n an element of the natural numbers that 9 minus 59 is arithmetic. So for this, we do the same as the previous one, but we would take any term and its previous term, and we should get it equal to a constant. And of course, that constant we saw was d, the common difference. So rather than working out what are the first 5 or 6 terms by subbing in n is 1, n is 2, n is 3, n is 4, n is 5, we just literally take t of n, and wherever there's an n, we put n minus 1. So it's 9 minus 5n, so that's going to become 9 minus 5 times n minus 1. So that's 9 minus 5n plus 5. In other words, 9 and 5 is 14 minus 5n. So now we have t of n, and we have t of n minus 1. So what we do next is we subtract them, and we should get a constant. In other words, there should be no n in our answer if this is an arithmetic sequence. So we have 9 minus 5n minus 14 plus 5n. And we can see our n's cancel, leaving us with n minus 14, which is minus 5. So therefore we say t of n minus t of n minus 1 is equal to a constant, hence arithmetic. And the common difference is minus 5. So here in this example, we have to investigate. So investigate implies that it may or may not be arithmetic. So we have t of n is equal to n squared plus 2. So I must get t of n minus 1. So wherever there's an n, I replace it with n minus 1. So therefore that's going to be n squared minus 2n plus 1 plus 2, which gives me n squared minus 2n plus 3. So now what I want to do is get t of n and subtract it from t of n minus 1 and see, do I get a constant or not? So t of n is n squared plus 2. T of n minus 1 is n squared minus 2n plus 3. And that gives us n squared plus 2 minus n squared plus 2n minus 3. So we have n squared minus n squared is 0. And I'm left then with 2n minus 1. So therefore, that is telling me that the difference between any two consecutive terms is not constant, because depending on what n is, then that means the difference is constantly changing. So if n was if n was 1, we'd get the difference between the terms would be 1. If n was 2, the difference between the terms would be 4 minus 1, which is 3, and so on. So therefore the difference is not constant, and therefore we say hence t of n equals n squared plus 2 is not an arithmetic sequence. So you're going to pause the video now, and for the first class you're looking at page 203, and you're going to be looking at linear graphs and then investigating if sequences are arithmetic or not. So on page 203 you'll do 11, and you can do that by observation, so you can write those into your book just by looking and seeing is there a constant difference between each of the terms. Question 12 you'll have to do into your copies because obviously you're going to do tn minus 1. Then 14 and 15 is just observation from the graphs. Then 17 and 18 you're going to have to check T2 minus T1 is equal to T3 minus T2. And then in 24 you're just going to draw a graph and see is it linear, and again make your check your answers then from your graph.